This would be our last talk for this afternoon and for this term as well. The title of the last workshop would be Implementing Curriculum Learning in PyTorch. This has been discussed in the last lecture last Wednesday. We know that curriculum learning is a learning paradigm that trains machine learning models the same way that humans learn, by starting with the easier problems and gradually increasing the difficulty of the problems that you're solving. This strategy has shown to improve generalization and convergence rate for a variety of models in computer vision and even in other fields. This workshop that we're going to have this afternoon will go over the steps to implement curriculum learning using PyTorch. Both predefined and self-paced methods will be covered for this discussion. So the speaker for this particular workshop would be Christian. Christian Tia is an undergraduate student in the BS-MS Computer Science program at De La Salle University. His research focuses on automated diabetic retinopathy classification and how it can be optimized in low resource settings using smartphone-based fundus imaging. So I'm now giving the floor to Christian for the presentation.
All right. Hopefully I'm visible and audible. So yeah, thank you, Sir Aaron. My name is Christian Tia, once again, and I will be conducting a technical workshop on curriculum learning for image classification. So last week we covered the core concepts of curriculum learning, including its definition, the general framework, and the main categories of curriculum learning. So today we'll implement some of those methods and go over their performance against a baseline model trained using traditional methods. So just as a recap, curriculum learning is when you purposefully present the training examples to the model using a specific order, such that the model may benefit from that order. And so a curriculum is a series of steps where in each step you define a subset of the entire training set. Usually at the first step of the curriculum, you would start with the smallest and easiest subset. So this example here shows images selected, which are very simple because the background is very plain. It has clear definition between the subject and background. And there's very few objects in each image. And so at the first step, you'll start with those images, and then eventually at some point, once the model is determined to be mature enough, you'll present harder images and increase that subset until eventually you use up the entire training set. And hopefully by then the model will have is fully trained and converged. So yeah, we'll be implementing curriculum learning using the following libraries. So there's no real requirement on the versions, as long as they're up to date and compatible with each other. So I'll be using PyTorch. I recommend the CUDA version so that you can take advantage of your GPU if you have one. And then Torch Vision, NumPy, Matplotlib, sklearn. And so yeah, just very basic libraries that I think most of you already have. So if you, I'll go over the notebook in this presentation, and then I'll send the Google Drive of this notebook so you can explore it and experiment it on your own later. So yeah, we'll be using ResNet 18 as the model for all of our experiments. And this is the ResNet 18 model, which is without pre-training. So no ImageNet, no use of ImageNet, and no transfer learning here, so that we can just focus on the effects of curriculum learning itself. And I define the following function here to just very conveniently get the model. One thing to note here is that I do replace the final connected layer so that the output is 10, because we are using the CIFAR or CIFAR 10 dataset. And this is not the regular CIFAR 10 dataset. Instead, we are using the CIFAR 10 corrupt or C data set, and this is derived from the original CIVI-10 test set of 10,000 images. So the CIVI-10 dataset, which you can install using this link. I also have it here in the notebook for you to download if you would like later on. So what this dataset has is once you download it, it has these a lot of these files for each form of corruption. And so each of these consists of 50,000 images, where the first 10,000 images show the tested images corrupted at severity level 1. And the next 40,000 would just be that those same images corrupted to more severe levels. And there are different corruption methods. Oops, there's a typo there. There are different corruption methods that are available for us to explore here. Like Gaussian noise, we have motion blur, JPEG compression, etc. And so to visualize what these look like, I have here an example. This is index 1000 of the dataset. So index 1000, since that falls within this first bracket, it would be the tested image corrupted at severity level 1. That's this image. And to acquire the rest of these severity levels, we just have to add 10,000 multiplied by the severity level, since it's just the same image repeated across 10,000 steps. So yeah, this is an example of the corruption JPEG compression. And there are, if you want to look at some other ones as well, let's see, like brightness. You can just load that up, and you can see that the data set will have the brightness becomes more severe towards the end, gets brighter and brighter, and because it gets corrupted, you kind of lose details in the pixels. So it makes it harder for a model, or even like personally as a human, makes some of these images difficult since they're already 32 by 32 pixels. And if we add on corruption, it makes it even more difficult. And so my goal here in selecting this data set is to simulate a real world noisy data set where there can be like a distribution of severe to very severe noise in the images. And we can actually we can generate the distribution of severities to use from these images using the following function, where I just define a normal distribution, and then we multiply it by some tail factor. So tail factor here would be how heavy the tails would be. A heavier tail would mean there are more of those rare images, so more of those severely noisy images in your data set, and a lower tail factor would be less. So since there are 10,000 images here, 10,000 unique images, we'll be using a split of 80%, 10%, and 10% for our train test and val sets. I made the tail factor for the train severities greater, so the tails of this distribution are heavier, indicating that the train distribution is actually noisier than that of the real world use case. And this is just to simulate those scenarios where we don't have a perfect training set, and it doesn't really represent the distribution of the real world. So yeah, in this case, in the train set, we'll have 3,500 or just over of those severity level 1, and then gradually decreasing up to like less than excuse me, 500 severity level at the tail end. On the other hand, the val and test severities that we'll be using would only have very few of those very severe examples. So yeah, since the data set, the file itself consists of 50,000 images, I created this custom PyTorch data set that will allow us to pair just the unique index, so from 0 to 9,999 to a corruption level. So this will manually, or this will automatically acquire the specific index of a unique image at a certain corruption severity level. So we don't have to worry about like the actual indices, instead just worry about the unique image identifier and also the corruption level. So it does this using this equation. It's actually sort of similar to how I imagined it is like virtual and physical addresses. Like if you remember, CS opposite. Well, anyway, trauma. But yeah, anyway, this will just convert the virtual index of the unique image to the corruption level. So it'll jump those levels for us automatically. So the train test split function from sklearn is also used to just split up the randomly the indices from 0 to or from 1 to 10,000 of those images. So yeah, since we're using a 80, 20, 20, the test size here is 0.2. And then for the validation set, which is the test indices, which were originally 20% here, we're further splitting it to 50% so that it's 10%, 10% for the val and test set. And then we'll just load those up using that custom data set that I defined previously, and put them into data loaders like so, and we'll use batch sizes of 128. So yeah, just as a sanity check, I also have this function that will look at the distribution of the labels and severities per train loader. And this is just to look at if the labels are correctly balanced. So it didn't sample like too much of one class and then too little of another. And also that the severity distribution would follow that of the distribution we defined previously. So here we can see that it did, because the severity level of the train loader for the severity 1 is 3,577, so just over 3.5 here. So these line up as well, and so do the rest of these distributions. So yeah, sanity is checked. Next, we can just define our evaluate function. Very simple, just do a forward pass on the model using the specified data loader, and then you just calculate how many you did correct, or how many the model predicted correctly, and how many it predicted over the total. Sorry, so correct over total. That's just accuracy. So yeah, now we can begin to actually implement the curriculum learning. So if you recall last week, the curriculum learning design consists of two main parts. Number one is the difficulty measure, and also the training scheduler, because there are, when you say you want to train from easy to hard, there's two questions you have to answer. Number one, what is easy, what is hard? And also, when you move from easy to hard, how much more hard data do you introduce, and how much more per step? Okay, and those two questions are answered by these two modules, I guess, or two functions. And so I defined here a sort of generic train model function that can take in any difficulty measure function and training scheduler function, so that it's cleaner that way. We don't have to keep defining different loops just for different configurations. But this is just for the predefined curriculum learning. So predefined curriculum learning is when you as a researcher have some prior knowledge on the data set. Let's say you know that the data set consists of a lot of varying shapes. So if there is a shape present that is highly unusual, like let's say it's like a non-convex polygon, then that would be considered difficult compared to like a simple shape like a circle. So you as a researcher must have some expertise or some prior knowledge on the data characteristics of the data set in order to use predefined CL correctly or sufficiently. And the same goes for training scheduler. Will be determining or deciding before training begins how you move through the data set, or how much you increase the subsets throughout the steps. So if we look at this train model function, at first we just define some hyperparameters here. This just keeps everything consistent between each experiment, and we also define some trackers for the validation accuracy so that we can retrieve the best performing model at the end based on validation accuracy, and then do a final evaluation on the test set. And then we do the loop per epoch, set the model to train, and then if we do have these, the difficulty measure and training scheduler, then we can begin our acquiring that subset for our curriculum. So number one, we get lambda is equal to training scheduler. So lambda for predefined CL refers to the proportion of data, proportion of easiest examples that you will use at that step. So if we look at our predefined CL, let's look at this red line, which is called baby step. So this red line shows that at epoch 0 to 200, for this example, epoch 0 to 200, the lambda is 0.3. So only a third of the examples will be included. A third of the easiest examples will be included from epoch 0 to 200. And then since baby step is a discrete scheduler, it just jumps up to 0.6 at epoch 200, and it does the same at epoch 400. So it does so through these steps, hence the name. So we can define many different training schedulers or functions for lambda. As you can see here, there's root functions, linear functions, and geometric functions. And so yeah, there's a lot of variety here in predefined CL. So that's how you get lambda first. And then once you acquire lambda, or the proportion of the data that you'll use, then you can sort the training set based on the difficulty measure that you define. So in our case, the difficulty measure that we'll be using is on the severity level. So since we know that the data set has varying severity levels that we can use as a measure of noise or difficulty, that's what we're going to use as the difficulty measure. So yeah, this function, all it does is that it returns a data set where the entire train set is sorted according to the severity. So yeah, since the train set is now sorted and we know the proportion we want, we can just cut into that first slice of the sorted train set to get our proportion of easiest examples, since it is sorted, right? And that's what these lines do. And then once we have our subset, we just load that up into a data loader with the same batch size, and then start training. And this is just a very basic train loop as well, looping through the data loader, getting all the batches, and then yeah, calculating the backprop, and then stepping the optimizer. So yeah, at the end of that of those epochs, then you validate the model at that epoch. Say you perform the accuracy test on the validation set, and then just store that. And then if you find that that validation accuracy is the best out of everything, you store that as the best weights, or the current weights as the best weights, so that after all training, you can restore those best weights and evaluate the test, or evaluate the model on the test set, which is an independent set of data that's unseen to the model. So yeah, just as a baseline, we'll do traditional learning first, which does not perform difficulty measure and training scheduler. So we're not specifying any of those here, and since we don't specify any of that, we'll just go to this else statement, which will just load up the entire training set. So no curriculum here. So yeah, perform 50 epochs, and then we find that the test accuracy is 0.38. So it's actually quite low. And you can kind of see why if you look at the data set. So it's already very very low amount of pixels, and then you're making it even worse by adding those corruptions. So if you look at some other examples, this one, it's quite easy to see that it's a dog, just because there's a face and the shape, right? If you look at some other examples, like this is becoming quite abstract at this point. And it's hard to see even like as a human, like what they are. So it's understandable, especially here towards the end, you lose so much detail through the compression. So if there are a lot of those, like in the training set, it might be difficult for the model to adapt. So that's the reason why the test accuracy is quite low. And also considering that there's only 10,000 images that we're using, or 8,000 images for the training set. So the goal of this notebook is not really to do the best performance on this data set, but just to demonstrate how performance can be changed by implementing those curriculum learners. So yeah, after we do our baseline, we can do predefined CL. So at first we went over this already. We defined the difficulty measure to be using the severity level of each image. And then for our first predefined CL, we'll use baby steps. So like this discrete scheduler right here. We'll start at the rate of 0.5. So what that would look like is this example right here starts at a lambda of 0.3. So instead we'll start at a higher value, and then at every 10 epochs, we'd increase that lambda by 0.1. And that's what this function does right here. And also we cap it at 1.0 because since lambda is a proportion, it wouldn't really make sense to have greater than 1 proportion of the data set unless you're oversampling, I guess. So yeah, we pass those two functions into the train model function that we defined earlier. So right now we're using the discrete scheduler and we're naming it baby step. And then we can see that performance actually did not improve. It got worse on using baby step. And this highlights sort of one weakness of curriculum learning, which is that you need a lot of experimentation because the training scheduler and the difficulty measure are highly dependent on like lots of the performance is highly dependent on like hyperparameters and different factors, and there is no real methodology in how to select them. So you have to really explore different methods, different functions to see if you can improve the performance. So let's try something else. Instead of the discrete scheduler like this one, we'll use a pacing function so that we use a continuous function for lambda. So in this case, we're using, we have two here. We have one linear. So that would be this straight line right here, this dark blue. So as the epochs increase, so too does the lambda at a steady linear pace. And we also have another example here with P, which is much more complicated at first glance. But all it does is just takes the root of the starting lambda raised to P plus 1 minus the starting lambda raised to P again over the T grow. And T grow here would be the epoch at which we want the curriculum to fully mature. So at this point, at T grow, we want to be using all of the data. So yeah, if we were to just implement these equations, it would look like this. So as you can see, lambda is equal to lam0 plus 1 minus lam0 over T grow times T. So you can see it's the same. Same for root P. And in this case, we're using root 5. If we want to visualize the functions the continuous schedulers that we defined for lambda, this is like an example that came from a paper that I have referenced below. But this visualization is now using our function directly. So this uses like sample epochs, and then it just calculates the values as outputted by these functions and then plots them. And as you can see here, root P, it starts off with adding a lot of proportion of the data, and it slowly slows down. So you could think that this has the benefit of sort of starting up or warming up the model faster because you're introducing those easy examples quicker. And then as you get into harder examples, then you can slow it down because it would take longer theoretically to learn the features from them since they are so noisy. And this is our discrete step that we used a while ago in our first example, the baby step. You can see that it follows this stair-like shape. And then we also have the linear function that we defined here. So this block right here would call on the train model function on the linear lambda function. So if previously we used the baby step, now we are using linear, which is this one. So the way at which we introduce the data. So if you look here, we're adding images much more steadier per curriculum step or per epoch, as opposed to the previous example of baby step. And as you can see, after training, the test accuracy is now 0.445. So not much better than the original performance of 0.38, but there is still some improvement. So yeah, we still have to explore some other options as well, because the improvement is not that significant. So now we're using that root function, shown by this orange line, and then performance now actually got worse. So yeah, this really shows the difficulty with predefined CL, since you do have to have like that expert knowledge on the data set. Right now we're just using the severity levels of the data set, and it seems that that's not that doesn't work that well for this specific data set using predefined CL. So to alleviate the pressure off of the researcher, another category of curriculum learning methods is automatic CL. So where in predefined CL, we have to manually define the difficulty measure and the training scheduler. Automatic CL would now use the student itself as the teacher. So predefined CL, we're the teacher, we're defining the curriculum. However, automatic CL, now the student has some input on how that curriculum is set. Okay, so now the difficulty measure, where previously it was the severity level, where we defined it as a severity. Yeah. Now the difficulty measure is loss based. So each time the so the model, every time we want to sort the training set according to difficulty, we will do a forward pass using that student model, and based on their loss on each example, that's how we determine difficulty. So if the loss was a lot, then we could think, okay, this is difficult for that student, let's consider it difficult. And if the loss is very low or zero, then that would constitute an easy example. So that's all this function does, is that it does the forward pass, and it sorts the training set based on that loss that we calculate here. And another feature of automatic CL is that instead of so this is sort of similar to Lambda, where previously it was the proportion of data that we want to include. However, now here in automatic CL, it's thought of as weights. So if a model would have loss of 0.4, if we were to use a hard regularizer at lambda equals 0.8, all examples which have loss of less than 0.8 would have a full weight, so 1.0. And all of those that are greater than that threshold of lambda would have weight of 0. That's why it's called a hard regularizer. On the other hand, there's also soft regularizers, such as this linear one, which would consider only the easiest examples to be a full weight, while the in-between ones are gradually lowering. The in-between ones have gradually lowering weights in them. So yeah, this visualization is just based on these two functions that I defined here. The hard regularizer will just compare the loss and the lambda. So losses here is like an array. So you can simply just do this is like a conditional and then convert it to a float. So if the loss is less than lambda, this would be 1.0 because it's true. So this is all 1.0 here, and then the rest would be 0.0. And the linear regularizer will just perform this linear function right here. So another aspect of these automatic CL, sorry, let me just find the framework. Another aspect of these automatic CL is that you need to define a different way of defining the lambda lambda schedule, because now it's not just proportion, so it's not from 0 to 1. You can go much more beyond 1, because lambda now represents the threshold for loss. So if we were to just limit the lambda to 1, then it's unlikely that our model would weight a lot of examples as highly, because at the start of training, of course, our losses would be very high. So it would be very rare to have losses less than 1.0 there. So this lambda scheduler is linear. So once again, I just outputted displayed the outputs of this function using this graph. So it would go from the starting lambda of 0.2 all the way up to lambda of 5 at epoch 50. And then, so now we have defined a new function for training the automatic model, where instead of using subsets, now you just apply the weight of an example when you're calculating or when you're doing the back propagation. So here we calculate lambda based on the scheduler as shown here. And then when we're training, we get the loss, and then we calculate the weights based on that regularizer that we define, either hard or linear. So if it is the hard regularizer, then it's either just 1 or 0. And we get those weights, and then we then calculate a weighted loss. So now the loss that the trainer would use to perform back propagation is not the full loss, but instead weighted. So if weight is 0, so those examples would be like removed, so they're not represented at all, and so the parameters aren't adjusted based on them, so to speak. So yeah, this is where you apply those weights, and then you perform backwards propagation based on that weighted loss instead of just the basic loss, and then you do the same evaluation. And if we perform the training on using automatic CL on a hard regularizer, we can see that it starts off slow. So warm up for automatic CL or self-paced learning specifically is quite slow, because since the student is the teacher at the start, the student is quite dumb, I guess. So it doesn't really know what to consider hard or easy, since the weights have just been initialized. But once it starts to warm up, then performance starts going up and up. And actually, test accuracy for the hard SPL or hard self-paced learning curriculum learning is the highest, with accuracy of 0.501. So that's 0.6 or 6% better than the baseline model. So yeah, this is a summary right here of the test accuracies using the different methods. So these 3 right here are predefined CL, and then we have one automatic CL, which performed the best. And this goes to show how difficult it can be to find the correct parameters. But if you do find the best fit for your model, either like automatic CL or predefined, then you could see gains in performance using curriculum learning. So yeah, that concludes my presentation for this notebook. I'll send the link in the chat now for the dataset and for the Google Drive.
Thank you, Christian, for the presentation. We have questions from the listeners. We have a question here from Claire. The question is, do you recommend trying automatic CL or predefined CL first?
Yeah, so that's a good question, because everything is sort of trial and error, right? You want to try to save time by finding like the most optimal method first. I would say that between automatic or predefined CL, your decision would be highly based on your knowledge on the data set. So let's say if the data set is in the medical field, so they're medical images, and you have like domain expertise in the form of like a doctor who can recommend like a method in defining what a difficult medical image is, like in an X-ray, for example. Then I would recommend you try predefined CL first, because you could leverage that domain expertise. On the other hand, if you are sort of unfamiliar, or like the data set is very large and then highly variable, and it's hard to find a predefined difficulty measure, then I would recommend to start off with automatic CL first, so that you can pass on that responsibility to the automatic difficulty measure, and so so it's also more flexible that way, because the difficulty measure adapts based on the performance of the student model. So yeah.
Okay. Any other questions from the listeners? If you have no questions, maybe you would like to raise your hands, please. Okay. So I think there are no more questions from our audience for this afternoon. We thank everyone who presented this afternoon: Christian, Rafael, Aaron, and Ryan, for the workshop presentations that you presented. And we thank those who attended our lecture and our workshop for this term. This would be the last workshop and lecture for this term, and we're going to have a new batch or a new set of lectures and workshops next term. Thank you again, everyone, and I do hope that you learned a thing or two about the things that were discussed, especially on detection and classification. Thank you, everyone. Have a great week. Ingat kayo.